Welcome back to the deep dive. Today, we are doing a bit of, let's call it digital archaeology.
Archaeology. I mean, in this field, that usually means looking at a paper from, what, 6 months ago?
Fair point, yeah. But today, we're actually going all the way back to early 2020, the pre-pandemic world. We are looking at a paper that I honestly think is one of the most underappreciated architectural breakthroughs of the last decade.
Oh, absolutely.
It's called Reformer, the Efficient Transformer. And this is by Kitaev, Kaiser, and Levskaya from UC Berkeley and Google Research.
It is a total classic. And you're completely right to call it underappreciated because, everyone is obsessed with the latest GPT or Gemini release. But this paper, this is part of our Foundations of Gen AI series for a reason. It tackled the fundamental plumbing of how these models actually work.
Right.
They were trying to solve the memory wall.
The memory wall. That is definitely a villain of today's story. Because here's the thing. For everyone listening, we all love transformers. They write code, they summarize emails, they generate art, but they are incredibly deeply wasteful.
Yeah. Hungry is the polite word. Inefficient is probably the accurate one.
Exactly. So the mission for this deep dive is to figure out how the Reformer architecture managed to process sequences of 64,000 tokens, which is, that's like reading a whole novel in one go on a single machine.
Without crashing it.
Without crashing it. And they did it by basically breaking the traditional rules of how transformers pay attention.
It really is a masterclass in algorithmic efficiency because they looked at the standard transformer and essentially said, you are doing way too much math for things that just do not matter.
So let's set the stage a bit. It's 2019. The race is fully on. Everyone is just building bigger models. We're seeing models with 500 million parameters per layer.
Which, by modern standards, sounds almost quaint. But at the time, that was a monster model.
Right, exactly. And the assumption was always just bigger is better. More parameters equals smarter AI. But I was looking at the math in the paper, and there's a catch that nobody really talks about.
The hidden cost.
Yeah. If you have a 500 million parameter model, that takes up about 2 gigabytes of memory just to store the weights.
Right. So if you're a researcher and you have a standard gaming GPU with maybe 16 gigabytes of VRAM, you're thinking, I'm fine. I have plenty of room for 2 gigabytes.
But you don't, because the model doesn't just need to store what it knows the parameters. It needs to store what it's thinking about right now.
The activations.
The activations. Let's actually unpack that term because it sounds super technical, but it is crucial to this whole problem.
Think of it this way. The parameters are the textbook the student has memorized over years of study. The activations are the scratch paper the student uses while solving a specific math problem right in front of them.
Oh, I love that analogy.
So if the problem is short, like what is 2 plus 2, you don't need much scratch paper. But if the problem is summarize this 300-page legal document and cross-reference it with these 5 case files,
you are going to need a lot of scratch paper.
Stacks of it. And in the transformer world, that scratch paper is incredibly expensive.
The paper points out that for a sequence of 64,000 tokens, the activations for just one layer can take up another 2 gigabytes.
And remember, deep learning models are deep. They aren't just one layer. They're 12, 24, sometimes 100 layers.
So you do the math. 2 gigabytes per layer times 12 layers. We're already 24 gigabytes. Plus the parameters. We have completely crashed our consumer GPU.
Yep.
We're getting the dreaded out-of-memory error.
Precisely. And that's the tragedy the authors point out right at the beginning. They explicitly say that even though the data sets, like the entire text of Wikipedia, are small enough to fit on a cheap hard drive you can buy at a local store, the actual process of training is so memory-intensive that it pushes research out of universities and startups.
It becomes a game only the massive tech giants can play.
Purely because of the hardware costs.
So the Reformer is basically trying to democratize AI by making it leaner. And they identify 3 main villains causing this memory explosion. And the biggest one, the one everyone in the field fears, is the big O of L-squared complexity tension.
The dreaded quadratic explosion.
Let's demystify this for a second.
Yeah.
L is the length of the sequence.
Yeah.
Why is it squared? Like, why is that such a massive problem?
It comes down to how standard dot product attention works. This is the mechanism that lets the model understand context. If I say the word bank, the model needs to look at every other word in the sentence to know if I mean a river bank or a financial bank.
So it compares bank to every single other word.
Yes. Every token is compared to every other token. Imagine being at a cocktail party with 10 people. You can shake hands with everyone pretty easily. That's 100 interactions if everyone shakes hands with everyone else. Totally manageable.
But if you have 64,000 people at the party,
You are doing 64,000 times 64,000 handshakes.
which is, let's just think about that, roughly 4 billion comparisons.
Just for one single step of the model.
Wow.
And you have to store the result of every single one of those 4 billion handshakes in a massive grid called the attention matrix.
That is just absurd.
It really is. If you store that matrix in standard 32-bit floats, that single grid takes up 16 gigabytes of memory. Just for the attention map. That's your entire memory card gone, just to figure out who is looking at who.
So it effectively breaks the model for long sequences.
Exactly.
So the reformer team stepped back and asked a very smart question. Do we actually need to shake hands with everyone?
Right, because they realized the matrix is actually sparse. Meaning for the word bank, 99% of the other words in the book, like the A or totally unrelated sentences pages away, are irrelevant.
You just don't need to pay attention to them.
Exactly. It's the needle in the haystack problem. Standard attention checks every single piece of hay to find the needle. The reformer wants to filter out the hay first.
Which brings us to their first big solution, LSH attention, locality-sensitive hashing.
This is the core breakthrough of the paper.
But how do you know which words are relevant without checking them all first? I mean, it feels like a chicken and egg problem.
Yeah.
You need to know they're similar to group them, but you need to group them to check if they're similar.
And that is exactly where the hashing comes in.
Okay, so I was looking at figure 1 in the paper, and it shows these points projected onto a sphere. Help us visualize this. How does hashing solve the cocktail party problem?
Okay, let's go back to the party. Imagine we want to group people by their interests. But we can't interview all 64,000 of them. So instead, we play a game. We draw random lines on the floor. Or, in the 3D visual from the paper, we slice the room with random planes.
Kind of like slicing a pizza.
Yeah, exactly like slicing a pizza. We slice the space up. Now, the mathematical theory here is, if you and I are standing right next to each other, meaning our vectors are mathematically very similar if someone slices the room randomly, we will probably end up on the same side of the slice.
We end up in the same slice of pizza, the same bucket.
Right, we fall into the same bucket.
And if someone is on the totally opposite side of the room, they end up in a different bucket.
Exactly. So instead of comparing everyone to everyone, the model assigns a hash code to every word based on which bucket it fell into. Then it just sorts the words by that code.
So now in the model's memory, the word cat is sitting right next to the word kitten because they landed in the same exact bucket.
And here's the magic trick. The model only performs attention to handshakes on the words that are in the same bucket. It just completely ignores the rest of the 64,000 words.
That is so clever. You've turned a massive global search into a tight local search.
Exactly.
But, and I have to play devil's advocate here for a second.
Please do.
You said random slices.
Yes.
What if I just get unlucky? Like, what if cat and kitten are neighbors, but the random slice goes right exactly between them?
That does happen. It's probabilistic. If you only slice the room once, cat ends up in bucket A, and kitten ends up in bucket B, and they literally never talk. The context is totally lost.
That seems like a pretty massive flaw for an AI. Like, sorry, I missed the context of this entire chapter because of a bad dice roll.
Which is exactly why the reformer uses multi-round LSH. They don't just slice the room once, they shuffle the angles and slice it again. And then again.
Ah, okay, so maybe we get separated in round 1, but in round 2 or round 3, we fall into the same bucket.
Exactly. The paper shows that with just 8 rounds of hashing, the model catches almost all the relevant connections. It matches the performance of full quadratic attention, but with a tiny fraction of the compute cost.
It changes the math from L squared to LlogL. That's the difference between a curve that shoots straight to the moon and a line that stays almost flat as you scale up.
It's massive. But there is a weird technical quirk here we should definitely mention because it honestly confused me when I first read it years ago.
Oh, the shared QK thing.
Yes. To make this bucket sorting work efficiently, they had to change how queries and keys work in the attention mechanism.
Yeah, I saw that. Usually in a standard transformer, a token has a query vector, which is what it's looking for, and a key vector, which is what it defines itself as. And these are usually distinct.
Right. Think of it like a literal lock and key. The key doesn't look like the lock. But for LSH to work to guarantee that the query lands in the same hashing bucket as the key it needs to find, they force them to be identical. Q equals K.
That sounds really restrictive, like saying I can only find people at this party who look exactly like me. Doesn't that hurt the model's ability to learn complex relationships?
You would absolutely think so. It was a huge gamble. But they ran the experiments, and surprisingly, It didn't hurt performance at all. It turns out the model is flexible enough to learn a shared representation space where lookups still work perfectly fine, even if Q equals K.
Wow. Okay, so we've solved the attention bottleneck.
Yeah.
We can process long sequences without the memory exploding.
Right.
But we still have that other problem we mentioned at the start.
Yeah.
The depth problem.
Right, the layers.
Mhm.
Storing the activations for every single layer so we can do backpropagation later.
Which brings us to solution number 2, the reversible transformer, or revenants.
This is genuinely my favorite part of the paper. It is just so elegant.
It felt like black magic to me when I was reading it. They claim they don't need to store the history of the layers because they can just, calculate it back into existence?
It's not magic, it's just algebra.
Okay, walk me through this. Because in a normal network, I pass data from layer 1 to layer 2. I have to save layer 1's output in a cache so I can use it later for training.
Right. That's the breadcrumbs approach. You leave a trail of data so you can find your way back during the learning phase. RevNests just get rid of the breadcrumbs entirely. They use a special architecture where if you have the output of layer 2, you can run a reverse mathematical operation to perfectly reconstruct the output of layer 1.
So you don't need the cache at all. You just look at where you are, run the math backward, and figure out exactly where you came from.
Exactly. It relies on a technique from an earlier paper by Gomez and colleagues. It splits the input into 2 parts and uses a very specific equation. Basically, y1 equals x1 plus a function of x2.
Okay, we don't need to parse the algebra too deeply here on audio, but the intuition is, because it's a simple addition of a function, you can literally just subtract it to go back in reverse.
Precisely. Subtraction is just the inverse of addition. It is really that simple. By structuring every single layer this way, you do not need to store the inputs in memory. You just recalculate them when you need them.
And what's the actual impact on memory when you do that?
It means the memory cost for activations becomes independent of the number of layers.
Independent of the number of layers. That is a wild sentence in machine learning.
It really is. It means a 100-layer model takes roughly the exact same memory for activations as a 1-layer model.
That effectively makes depth free in terms of RAM.
In terms of RAM, yes, but remember, there is no free lunch in computer science. What are we paying for this?
I assume time.
Exactly time compute cycles. Because you aren't retrieving the data from a fast memory cache, you have to physically recalculate it during the backward pass.
Right.
So you are essentially doing the math twice. It makes the training process about 30 to 40% slower.
But you can actually fit it on one GPU.
Right. You trade time for space. If you have infinite money and a cluster of 1,000 GPUs, maybe you don't care about memory. But for everyone else, being able to train a really deep model slowly on one card is vastly better than not being able to train it at all because you instantly ran out of memory.
Okay, so we have LSH to fix the quadratic attention width. We have reversible layers to fix the depth memory.
Yeah?
There was one small third fix mentioned in the paper too. Chunking.
Yes, chunking. This addresses the feed-forward layers. These are the thick middle parts of the sandwich in each transformer block. They can be very wide, like 4,000 or more dimensions.
And if you push 64,000 tokens through a 4,000 wide layer all at the same time, you create another massive memory spike.
Exactly. But the insight here is super simple. The feed-forward layer doesn't mix information between tokens. The word cat is processed completely independently from the word dog in the specific layer. They aren't shaking hands here.
So you don't need to do them all simultaneously.
Right, you can just chunk it. Process the first 2,000 words, save the result, clear the memory, process the next 2,000. It's just simple batch processing inside the layer itself.
Brilliant. So let's recap where we are. We have LSH to fix attention. We have reversible layers for depth and chunking for the wide layers. They built this thing, the reformer. Now the million-dollar question, does it actually work? Or is it just a really cool theory that falls apart in practice?
Oh, it works. They put it to the test on a few specific tasks. The first was a synthetic duplication task. You give the model a string like 0W, 0W, and it just has to repeat the second half perfectly.
Which a standard transformer does easily.
Very easily. And the LSH reformer does it perfectly too, as long as you use enough hash rounds, usually 4 or 8 rounds. But the more telling test was real-world data. They used NWIC8, which is a text modeling task using Wikipedia data. They fed it sequences of 64,000 characters.
And how did it compare to a standard power-hungry transformer?
In terms of bits per character, which is how we measure accuracy or basically smartness in this task, it completely matched the baseline.
So it didn't get stupider. It just got way more efficient.
Correct. And there's a graph in the paper, figure 5, that I think should be framed on the wall of every AI lab.
Oh, is that the speed versus length graph?
Yes. It plots how fast the model runs as the input sequence gets longer.
Yeah.
For the standard transformer, the line just curves upward exponentially. As the sequence gets longer, the model grinds to a complete halt. It hits a wall.
And the reformer's line?
Flat, practically linear. Processing 64,000 tokens takes roughly twice as long as 32,000. Not 4 times as long, not 10 times as long, just twice.
That scalability is everything. They also mentioned they could train a 20-layer big reformer on NWIC 8 on a single core. That is the democratization we talked about earlier.
And they didn't stop at text. They also tested it on ImageNet generation, generating images pixel by pixel.
Which is basically just a really, really long sequence of numbers if you unroll an image, right?
Right. If you treat an image as a sequence of pixels, standard 64 by 64 image is 4,096 tokens. But if you try to go bigger than that, the standard transformer just chokes. The reformer handled it comfortably.
So stepping back for a minute, this paper is from 2020. Why does this matter to you, the listener, today? We have GPT-4 now. We have Gemini with million-token context windows. Did the reformer win?
Well, yes and no.
Yeah.
We don't necessarily use LSH attention in every single model today. Things like flash attention, which optimizes how the GPU actually reads and writes memory at the hardware level, have become the industry standard. But the fundamental principles here are totally foundational.
It proved that the brute force approach wasn't the only way forward.
Exactly. It proved that sparse attention actually works. It proved that you don't need to hold the entire history in memory to learn deep representations. It really opened the door for long context AI. Before this paper, we were stuck generating a few paragraphs at a time. The reformer showed us we could theoretically generate chapters or process entire legal contracts or analyze whole genomes.
It shifted the focus from how much VRAM can I possibly buy to how smart can I design my architecture.
And that is a shift we still desperately need today. As models get into the trillions of parameters, we can't just keep buying more H100s forever. We have to get smarter about the math.
I completely agree. And I actually want to leave the listeners with a final thought that really struck me while I was rereading this paper. It's about that LSH approximation.
Oh yeah, go on.
The paper freely admits that LSH is an approximation. It's throwing darts. It might miss a connection here or there. It's probabilistic. It is not perfect.
True, it's a kind of fuzzy logic.
But the model still learns just as well. It matches the performance of the full, perfect, computationally expensive attention matrix.
Almost exactly identical. Yeah.
So here is the provocative thought for everyone listening. If we can approximate attention, which is supposedly the very soul of this technology, the thing that makes it smart by just throwing words into random buckets, and we lose almost nothing in performance. What does that say about standard transformers?
That is a deep question. It suggests they are incredibly inefficient by design.
Are they just calculating noise?
It definitely implies that the real intelligence of these models is much, much sparser than we tend to think. We force them to calculate a fully dense matrix of relationships, checking every single word against every single word, but maybe 99% of those calculations are just zeros waiting to happen. They're meaningless.
It honestly makes you wonder if the human brain is an LSH machine. We certainly don't pay attention to every single pixel in our vision or every background sound in a room. We bucket things, we filter, we ignore the noise.
And we seem to do just fine. The reformer might actually be a step closer to how biological intelligence actually manages bandwidth. We don't have infinite memory in our heads, so we have to be brutally efficient.
Less is more. It is a fascinating look at the underlying plumbing of AI, and a great reminder that sometimes the best solution isn't just throwing more raw power at a problem, it's bringing a sharper knife.
Well said.
That is a wrap for this deep dive on the reformer. Thanks for geeking out with us.
Always a pleasure.
We will catch you on the next one.